Now we are going to calculate electric field due to a charged rod. So we have taken a uniformly charged rod which is positively charged, and along its axis there is a point which is along the axis of this rod, and at this point we have to find out what is the electric field due to this entire rod. Now in order to find electric field, we have two expressions. One is for a point charge, which is electric field is equal to Ke q upon r square, which is due to a point charge. But now this is not a point charge and it is an extended object. So in order to find out the electric field due to this extended object at this point, we'll be using an expression which is electric field is equal to Ke integral of dq upon r square, and if it is a vector you can use r unit vector. So at this point, because it is a positively charged object, so from intuition we can say that the electric field will be away from the object and it will be directed along the radius. So from this point to this point, electric field will point towards this direction. Okay. Now in order to solve it, because we are working on the small charge dq, let us say that we divide this wire into small parts, and let us say that one of these parts has a length of dx and it has a charge of dq, the small length of the object. Now the total charge of this entire rod is q, and the entire length of this rod is given to be L, and it has a total charge of Q. And what is known is that the charge density, which is the total charge upon the total length, is a constant. So if it is a constant, it means that it can also be written as the small charge upon the small length of this wire will also be equal to lambda. So if we have to find out the electric field, let's say that we need to find out the magnitude of the electric field, it will be integral of dq upon r square magnitude and the electric field magnitude. So from here we can say that dq will be equal to lambda dx. Also, let us denote these distances. It's known that this distance from the end of the rod to the point is given by a, and the distance of the small part of the wire from this origin point is x. So then, if we know all these distances, the expression for electric field turns out to be, let me write it here, that electric field will be given by the Coulomb constant integral of dq can be replaced by lambda dx upon r square. Now what is r? R is the distance of the charge from the point where we want to know the electric field. Now in this case, this is the point where we want to know the electric field, and this is the charge which is under consideration. So the distance from this charge to this point should be x. So it will be divided by x squared, and the limit of integration should be, now we have to integrate it over x. Now x should be from a to L plus a. So the limit of integration will be from a to L plus a. So then if we integrate it, it will be ke. Lambda can be taken outside because we know it's a constant. So x square can be taken to the numerator. So it will be minus 2 plus 1 minus 2 plus 1 from a to L plus a. So this will be equal to and minus 1 upon x a to L plus a. And so it could also be written as ke lambda minus 1 upon L plus a plus 1 upon a, which will be equal to ke lambda minus a plus L plus a divided by a into L plus a. So these terms they cancel and we are left with ke lambda divided by a into L plus a into L. Now this term lambda into L, it can be taken from this equation and it is equal to the total charge on this wire, which is given by capital Q. So it will be a L plus a. So this will be the expression for electric field due to a uniformly charged wire at a point which lies at the axis of the wire.